we are going to be talking about wireless network at stadiums. We are going to start by talking about stadiums. Why stadiums are attractive for dedicated wireless network. We'll talk about general design requirement for stadiums. We'll see areas that are targeted for coverage for both inside the stadium and outside the stadium. Then we'll see best practices. When talking about best practices, we'll talk about site surveys, RF surveys, CW measurements. We're talking about 3D modeling. Why we want to spend hours modeling these venues. How detailed modeling actually pays off in the long run when it comes to the propagation analysis. After that, we'll go through the sectorization. Why we need it. We'll also see other stuff that is involved in designing and deploying the network. Then we'll focus on the capacity dimension. In the end, we'll give examples of RF coverage maps and the KPIs. And then we will summarize what we have learned. So, hi friends, again, good morning, good evening, according to your time zone. It's so good to see you all again. This is Gaurav Goyal. First of all, thanks a lot for joining this session. I will try my best to make every second of your worth through this session. Again, this is me. My name is Gaurav Goyal, and I have been in telecom industry for over 18 years, mostly in the wireless industry, and I have worked in telecom in one capacity or another. So I have worked for all the largest telecom service providers in US like Verizon, AT&T, T-Mobile, etc., and also with major vendors like Nokia, Ericsson, Huawei. And in addition to that, I worked with Infovista as product manager and solution consultant for their Planet tool. And I have done various certification related to 5G and in-building. And right now I'm IB-Wave level 3 certified. And before coming to US, I have worked in various companies and in various countries like India, Nigeria, Japan, Finland, UK, etc. So much of that time has been spent in the wireless networks only. And I have begun my career with 2G and now working with 5G for last 4 years. So at this moment, my focus is on 5G, Python, ORAN, and the in-building solutions. And I'm working with in-building solutions for many years, maybe more than 10 to 12 years. Okay, friends, this is about me. For more details about me, you can check my LinkedIn profile. So these are my past ID cards. So as I said by Albert Einstein, that only source of knowledge is experience. So try to learn and gain as much as experience as possible. I love this quote that don't be afraid of going slowly. Be afraid of standing still. So if you're not learning anything new, be it at professional level or at personal level, then it means you are standing still. This can cost you a lot in the long run. So you should start learning something new every day of your life. And before jumping to topic, I want to say one thing. Your involvement in the class is critical for you to benefit most from this webinar. I request you, if it is not absolute necessity, then please close your Outlook, social media, Facebook, WhatsApp, etc. if possible. Because it's a proven fact that there is no such thing in the world called multitask. Even a genius can't do two tasks at the same time. So it's my kind appeal to everybody. Please close all kind of social media or any kind of distraction. Okay. So are you with me? If yes, then please write yes in the chat box and then we can begin. Please write yes in the chat box. So these are the few acronyms. You can see it later. So let's talk about stadium first. So what is stadium? So stadium is a venue which consists of a field or track surrounded by a ball-shaped sitting area. The largest stadium in the world is Narendra Modi Stadium with sitting capacity of around 132K, and it is in Ahmedabad, Gujarat, India. And the second biggest is in Pyongyang, the North Korea. Sitting capacity is around 114K. So there are only a handful of stadiums with more than 100K seats. So stadium is a complex design as it has various kinds of areas and each area has different requirements. For example, it may have general public retail shops and the concession stands, which may be at the first level. On the same level, but not accessible to the general public, are the conference rooms. One level below is the ground level where the press rooms and team dressing rooms are located. As I said, due to their location inside the stadium, each area has different needs. The existing RF coverage coming from surrounding macro sites is fair in the ball area, but maybe poor below it, be it in the back office, in the conference room, and in the concession area. The macro sites that cover the stadium report high blocking during the venue event. That's why we need IBS solution for the stadium. You will get the good return of investment because stadiums have many spectators, but they are also the most complex to design. So different types of stadium. Again, what is stadium? A stadium is a venue for mostly outdoor sports, concerts, and other events, which consist of a field or a stage. First type of stadium is dome. So dome is a covered stadium for the outdoor sports. And then we have arena. So arena is mostly designed for indoor sports. And the third one is open, which is our conventional stadium. So you should understand these terms as it mostly used in our design. So first of all, as I said, a stadium is a typically an open air or partially covered venue that is designed to accommodate large area. It usually features tiered seating arranged in a circular or oval shape around the central field or a playing area. Stadiums are commonly used for outdoor sports like football, soccer, baseball, American football, and athletics, right? And stadiums can accommodate tens of thousands or even hundreds of thousands of spectators depending on their size. But on the other hand, an arena is typically an enclosed venue with a roof and walls that surround the playing area. Arenas are more versatile and can host a wider range of events, including indoor sports like basketball, ice hockey, indoor track, and the field. They are also used for concerts, exhibitions, conventions, and other large scale gatherings. So, arenas usually have fixed seating arrangements, often in a ball or U shape, providing good visibility to spectators. So, in summary, there are few differences. So, stadiums are open, but arenas are the enclosed venue. Stadiums are primarily used for outdoor sports, but arena may be used for indoor sports. And stadium have like large capacities, but arena generally smaller or medium sized capacity. So these are the few differences between arena and stadium. One more term you should also know is the amphitheater. Right? An amphitheater is a circular or oval shaped open air venue with the tiered seating. It is arranged in a curved or a elliptical manner. So it usually surrounds a central performance area. So amphitheater are historical known for hosting events like gladiator concert, chariot races, etc. So the most famous amphitheater is the Colosseum in Rome. So amphitheater are designed to accommodate a large number of spectators, also providing good visibility of the events in the central area. So arenas, stadiums, and the amphitheater are all types of venues used for various events, but they have distinct characteristics and the purposes. So you should be familiar with these terms if you want to do IBS design. So now the question comes, what makes a stadium so special? So as I said, stadiums are venues which are completely different from other in building scenarios. They have particular needs and the challenges. Any design engineer should understand these needs and challenges in order to create a suitable design. Because in stadium, people with different backgrounds, interests, and expectations meet in a stadium. And they should have sufficient wireless connectivity and the quality of service. So stadium is very special. So you can see here we have various community in stadium. So first community is visitors. So visitor comes to stadium for either an event, a match, or simply as a tourist wandering around the stadium. They normally make use of sitting area spaces, or in case of concerts, use of play field. During halftime periods or break, they might access food areas, bar areas, or toilets as well, right? So often some of them want to share the latest goal to their friends which can't come to stadium, and also they make use of their mobile devices to send streaming data, pictures, or SMS. Moreover, in stadium we have VIP visitors as well, so we have to take care of them as well. So sufficient coverage and capacity should be available in stadium for visitors, not only voice but also heavy data uses is there in this. Then we have stadium operations. So what is stadium operations? So stadium operations refers to the personnel who works for the stadium on daily basis. They also need to have coverage and connectivity, especially inside their offices. So they may include people who work at the front office, stadium maintenance staff, or the security guard. So they also need coverage and capacity. And we have event personnel. So what is event personnel? So event personnel refer to the people who works for specific event that is taking place at the stadium. For example, if it is a football match, the player may need coverage and connectivity in the dressing room, and they are mostly located in the basement. On the other hand, coaches and managers also need coverage in the play field. Also, referees need coverage, right? So these are the event personnel. Then we have this press and media. They also require coverage and capacity for press conference. Also, we have health and emergency services that also have strict requirements related to coverage and capacity. After that, we have security. So security refers to police services which patrol the event. They have strict coverage requirements with high service availability. Example of this can be Tetra in Europe, a private network used by the police. The areas where coverage is needed for security include even the most unexpected spaces in the stadium. So stadiums are special because they have special needs and the challenges. So stadium has special needs and challenges. Let's talk about some of the challenges for the stadium. So as I said, stadiums are challenging venues. So they require special radio design technique. First challenge is related to coverage. So first of all, as I said, stadiums have a mix of playfield area. For example, retail shops, concession stands, conference rooms, press rooms, team dressing rooms, etc. So this poses challenging environment for prediction of radio waves. Inclined surfaces on the areas have special effect on radio signal propagation. So that is also a challenge. Moreover, large mix of materials used in stadium for corridor. It may be open space, enclosed spaces, heavy penetration loss, walls, heavy duty construction, stair walls, lift shaft, etc. So stadium materials also make a penetration of signals difficult. Moreover, demanding coverage requirements in rooms such as VIP rooms, basement, dressing rooms, and car parks also require accurate radio planning and modeling. In short, you can say structure and architectural features make stadium unique and challenging. Then we have interference challenge. So around the stadium, we may have many macro cells that provide cellular coverage, right? And their signals can penetrate the premises of stadium as well. So if the interference management is not considered, a degradation in signal quality is expected from the macro signal. And one more thing, interference between wireless technologies should be also considered. So in case of stadium, there may be have various technology. It may be 3G, 4G, 5G, and various operators, maybe T-Mobile, Verizon, AT&T, right? So these interference issues should also be considered. Then we have capacity challenges as well. So it's not uncommon to see that stadiums host not only sports matches, but also concerts and other events. So this will bring a large number of spectators to be a potential wireless users for a limited period of time, typically for few hours. So there will be an increasing demands in the event days, but there may be decreasing demands in non-event days. So this clearly imposes a major load for operating networks, which needs to provide all resources, and they should guarantee a specific grade of services. The most critical thing is to balance traffic between event days and the non-event days, right? So because in stadium, we expect heavy data, so this makes a stadium challenging, because in the stadium we want to send some videos, share some pictures, downloading the replay of goals or touchdown, right? So thus, unlike other venues such as shopping centers, airports, capacity has different demands in stadium. So we need a unique strategy for stadium to design. And then we have issues related to handoff, passive intermodulation, and all these things we'll discuss in detail in next few. And we have these design requirements. Okay, so let's move to the design requirement. So typically in a stadium, all technologies, all network operators are present according to local market. So what we typically see? Well, we see those worldwide technologies such as UMTS, LTE, 5G, 3GPP technologies, right? We also see Verizon, T-Mobile, AT&T, etc. So we also see Wi-Fi deployed in hotspots, and then we also see public safety. So now, as a public safety, there is not a single technology associated with it. There are various ones depending on the part of the world. So we have to take care of these points as well during the design requirement. So first one is RF coverage. So the stadium network signal must be dominant throughout the venue. So if there are areas where existing macro coverage gives a 5-bar reading on a phone, even in those areas, building should be 5 to 7 dB stronger than the macro signal. And this requirement applies to the nearby transit areas like car parking, train station as well. The reason for this is that we want to provide the dominance of in-building signal at the venue. We do not want to dominate macro signal to avoid interference and the handovers. Moreover, we don't want to steal the capacity of a macro site. So macro coverage management, early days of stadium design. So early on in the macro network deployments, wireless service providers recognize the revenue potential of venues with high subscriber density like stadiums. At first, they tried to provide good stadium coverage, 5-bar coverage. This can be done by pointing sectors of nearby macro sites towards the venue. So what they are doing is they would say, okay, I'm going to build a cell site nearby. I'm going to point a sector towards the stadium. That is what going to give me a good coverage, voice coverage inside the stadium. Well, that worked quite well for a while. So earlier we are focused only on coverage. So the approach was low sector count, high gain sector panel antennas for ball coverage, lots of omnidirectional antennas for concourse coverage. So we may have strong signal from the macro sector that was pointed towards the stadium back in maybe in 2000, in 1999. But you want IBS to be dominant because in addition to coverage, you are concerned about capacity as well. So one approach is put many IBS antennas, but that will be an expensive solution. So now here in the figure, you will see a yellow area, right? This area where macro signal is very hot. So then a part of stadium is in the darker color. It basically means the signal is not so hot from that sector. So what to do for this yellow area? We want IBS dominance. So what to do with this yellow area? So, well, the easiest way is to down tilt that sector. The red line you see here shows the RF signal path with the initial antenna down tilt. The signal is diffracted from the stadium roof, which causes little attenuation. Thus, it will provide strong signal in the ball. But when the signal is down tilted, you can see this green line. The signal path in the green penetrates the concrete wall. So that is often preferable. Why? Because the concrete wall significantly attenuates the signal before it reaches the ball. So it is going to reduce the coverage for that macro sector. It is going to direct the RF rays to go through the concrete. That will basically reduce the macro signal level. So that is a technique to help with the macro coverage management. So two ways, either increase number of IBS antennas or down tilt macro site. So the effective way to reduce the macro coverage is to down tilt antennas at nearby sectors that are pointing towards the venue. Remember, here we are just talking about coverage, not capacity at this moment. Also, we can make some additional consideration as well. We can turn off the macro cells in the rare areas or so we can turn off macro cells in rare cases. Also, we can reduce power of macro cell. In addition to that, as discussed, we can adjust tilt and also we can change the azimuth of the macro cell. So let's talk about capacity. So as network becomes more data centric, the data traffic become more congested. So capacity inside of coverage at the venue becomes the primary concern. So nowadays, many stadiums have good coverage in the sitting ball, but needs a dedicated stadium network. So we must direct the traffic away from the neighboring cell site. Otherwise, macro sites will be overloaded, right? So the stadium network should be designed to address all services types from voice to streaming videos, because the pattern of voice and data calls may be different at stadium than at typically macro sites. Here in stadiums, voice call may be shorter due to stadium crowd noise. There may be far more file uploads to social media than usual, and some venue may limit streaming videos. For example, during 2014 Super Bowl, they ban it completely. So video streaming is completely banned. Right? So stadium had different capacity demands and the challenges. Then we have this interference management. So here in non-serving sectors are a source of interfering signals. Interference can be internal from non-serving dash sectors and external from the macro network. So minimizing interference improves both network capacity and maximize the achievable data rates. We'll see in few minutes the steps to reduce the interference. So now moving on to the handoff management. So first of all, as discussed, we want IBS to be dominant. So we do not want any handover with macro sites inside the stadium. So which will worsen the network performance. But handover is required, right? So IBS range is not very light, but handover is required, right? Because IBS range is not very large. So where to hand over? So there can be two options, maybe at the stadium entrance or maybe at the high traffic areas outside the stadium, right? So this is the, you can say, stadium entrance, and this you can say outside the stadium, right? So now whether we are going to hand over at a stadium entrance or at a high traffic area outside the stadium. So this is really a matter of observing the pattern of spectators before and after the game. For example, in North America, they tend to linger before the game quite a bit. In that case, you really would want to move the handover area away from those places where they tend to linger. Meaning, don't let them hand off at the tailgate area or a car parking lot area. Try to get the handover further away from there. And if it is more about European style soccer fan behavior, where they get in and get out of the stadium rather quickly, then the handover can be at the stadium entrance as well. What are the rules for the handoff management? So establish clear handoff areas between the macro network and the stadium network in the transit area outside the stadium. So once a subscriber hands off from the macro network, he should remain with the stadium network throughout the duration of his visit to the venue. Moreover, handoff traffic is controlled by the control channels. Therefore, extensive handoff traffic may use up control channel capacity, and it may result in call blocking even if the sufficient physical resources are available to carry voice and the data traffic. So handoff management is one of the important aspects that you should be careful. Then we have coverage areas inside the stadium. Now, as for coverage requirement inside the stadium, obviously the sitting area we need. But in addition to that, we also need to cover VIP boxes, or you can say corporate boxes, also TV commentators area. They are usually nearby, so they have to be covered. They are not typically open. Usually there is a glass that separates that area from the general sitting area. Then underneath the ball, what we have is the food and the drink concession area, and also we have shopping area. Usually they are located at the first level near the entrances, because that is the first thing that spectators go in, and they either buy a souvenir, food or drink. So what we have deeper down in the ball of the stadium is ground level. So here we have this ground level. So we have press rooms and dressing rooms for two teams that play. They have to be covered as well. So these are all hotspots that requires the coverage at the stadium. So we are not concerned only with the ball areas, but other areas as well during the stadium design. Therefore, capacity hotspots outside the ball area needs to be included in the design. It may be corporate boxes, it may be media boxes, it may be retail shop, it may be concession stands, it may be capacity hotspots like conference rooms, it may be press rooms. So all these rooms should be covered. All these hotspots should be covered. So these areas are generally well isolated from the sitting. So these areas are generally well isolated from the sitting ball. So they need their own antennas for coverage. And RF propagation characteristics in the stadium hotspot very considerable. Inside the ball, signal from dash is clearly in line of sight with UE. But in the back office, where the conference and locker rooms are located, ball density is much higher. So there is a significant non-line of sight propagation. So we should take care of these things as well during our design. Then we have this call blocking. As I said earlier, the existing RF coverage coming from surrounding macro site is fair in the ball area, but poor below it, like in back offices, in conference rooms, in the concession area. The macro site that covered the stadium reports high call blocking during the venue events. Anyone, what is blocking rate? Can you please write in the chat box? Cellular networks blocking occurs when a base station has no free channels to allocate to a mobile user. The macro sites that cover the stadium report high blocking rate during the venue events, during soccer events, football events, etc. So for this example, you can see here the blocking rate of 60%, right? In the busy hour peak, that is during the event. The call blocking problem is not restricted only to the stadium building, but also occurs in the stadium areas where spectators congregate before and after the event. These transit areas includes parking lots, train stations, pedestrian walkways, etc. Right? The stadium needs to provide coverage and capacity both to the stadium and to the nearby transit area. The network should be able to support traffic when the stadium is at full capacity during an event, and also the traffic near the venue before and after the event, right? So pretty much all the areas where spectators tend to linger before or during the game break. This is especially of interest in North America, where tailgating is prevailing phenomena in college football games and the professional football games. So we must take into account this as well. So going to game in North America is more of a half day experience as opposed to maybe 2 hour experience in the European soccer game. So the point is, although transit area outside the stadium have good coverage, they suffer from inadequate capacity before and after event. So the dash area should be extended to those areas as well. The dash has to be stronger than the residual macro signal. The aim is to guarantee that subscribers connect to the stadium network rather to the surrounding macro network. Right? Then let's talk about passive intermodulation. Why is passive intermodulation generated, or why it is not required? At high level, you can say that passive modulation is a kind of a noise, and we should avoid it as much as possible. So it is generated in neutral host networks when we have 2 or more signals that are belong to different frequency bands. So these two, when they mix, they generate the products called PIM, passive intermodulation, and it is also called as PIM. So those PIMs have lower amplitude than the original signals, but wider bandwidth. So you can see here in the picture that F1 has good amplitude, F2 has good amplitude, but due to this passive intermodulation, this third degree, fifth degree, seventh degree have wider bandwidth, but amplitude is very less, right? So, but we are more concerned about the amplitude. So again, where it is generated? It is generated in the passive devices, in cables and connectors, but also at the rusty boards near antenna. So rusty board is oxidized board, and that tends to affect the antenna patterns quite a bit. So how to avoid them? First of all, we should not use braided coax cables and N connectors because they are known source of pin. Instead, silver plated 7x16 DIN should be used. Also, avoid place antenna near the metallic objects, including the rusty board. Do not use equipment with unspecified PIM rate. And prior to antenna installation, on-site PIM testing should be used using antenna on pole. And this is covered in more details in my previous sessions as well. So these are the points related to intermodulation that we should be taking care of in future. So neutral host networks with high transmit powers are susceptible to passive intermodulation. And if PIM noise is sufficient high, it can reduce coverage, it can slow the network, it can cause drop costs, and it can reduce the battery life as well. So we should consider this as well during the stadium design. Now let's talk about best practices related to the site visit. First thing is the site survey. So site survey is one of the most important steps for design, especially for IBS design. And during the initial site visit, different kinds of information is gathered. Information about physical structure, architect, and the different morphology within the venue is gathered. A lot of information is captured in form of, you can say, photos, videos, and handwritten notes as well, measurement from various data collection tools, and the text annotation. So potential location at which to mount antennas, run cables, install equipment are also covered in the site survey. And during the survey, the existing macro radio coverage at venue should be recorded for all the wireless carriers. Also include all frequency bands of interest. So this is important part of survey because the actual stadium network has to overcome the macro coverage by a comfortable margin. Otherwise, UE may be registered with the macro network while at the venue. And this is a highly undesirable situation because our major requirement is to offload the macro network. So during the site survey, in addition to RF data, the engineers need to identify spots where antenna may be mounted, to identify a room big enough to house the head end, to identify a potential cable pass between the head end and the antennas. And recording the information directly onto a floor plan saves a lots of time. For that, you can use IB Wave Mobile. It helps information exchange with other departments and the stakeholder as well. So it's also important to identify several locations at which to mount antennas, because that can be used later on when you do the detailed RF coverage, right? Here you can see an example of data collected by an engineers during a site survey. So this is a photograph of a general area of a potential antenna location in the sitting area. So you can see that we want to, in this particular area, we want to mount antennas and we want to cover this particular area, right? So second figure, so this figure zooms in on the location and you can see a red mark where you can put your antennas. So the location needs to be identified on layout plan as well, so that the RF design engineers can know where they can put their dash antenna. So here you can see a red mark and here engineers is pointing that we should put our antenna in this particular area. And then in the third figure, you can see the venue layout displayed on a tablet. A red push pin indicates the antenna location. Trust me, when you are at the site, you remember everything. But the moment you reach office and start modeling, you forget everything. So these notes are very important. So again, our site survey is basically what you need to do when you first visit the site. Examine potential locations for head and room and the equipment, potential locations for maybe remote units and possible cable pathways. Also need to identify mounting place for your antennas. All that should be noted on a plan, preferably in a digital form, so that it can be uploaded in the cloud and shared with other engineers as well. So aside from the RF survey, so aside from the site survey, RF survey should be also performed, because we said that there may be a residual macro signal in at the venue. So we need to know how strong that signal is. So taking our RF macro surveys throughout this, the ball areas and also underneath in the shopping areas, also in the VIP boxes and also in the press and in the dressing rooms is a must. And now lastly, a CW test should be taken. So guys, what is CW test or what is continuous wave testing? Can you please write in the chat box? Okay, thanks for the right answer. So typically CW testing is the first phase of any RF planning. RF planning always starts with the continuous wave testing method for all greenfield projects. The main aim of doing CW testing is to gather information. And why to gather information? So that we can design a propagation model of transmitted signals for a mobile communication. So it is carried out to gather actual propagations of mobile signals in a different terrain or a clutter. So therefore, CW drive testing can be used for propagation model tuning. So if we identify possible location, we should try to put an antenna there and inject CW signal in there and then take CW coverage data. And this data then will be used to calibrate propagation model in a software tool of your choice. I have done many times in the IBWave tool, but you can do that in other tools as well. So like for macro, I have used ATOR tool and Planet tool for model tuning and asset tool. But for in-building, mostly I have used IBWave tool for this propagation model tuning. And if you can't put antenna on the exact location, then you can bring a tripod and try to place as close to the location where it is going to be as high as that location. So these are the best practices for site survey, RF survey, and the CW survey. Then we have this 3D modeling. So stadium 3D modeling, right? So with the help of this 3D modeling, we can verify the accuracy of the building more accurate, right? So it can be with respect to scale or alignment of walls and the surfaces. It helps simulate walking through the various floors to see the installed components and the walls. Moreover, it can be used as an image files for the documentation purposes. So this is an example, one of the 3D modeling I have done. So to this, you should have thorough knowledge of venue. So 3D modeling is not that easy thing, but you should have good knowledge of the venue. You should know which venue you are modeling, whether it's offices, hotels, shopping malls, stadiums, metros, subway. And what is model? Walls, floors, stairs, escalators, stadium sitting areas, building textures. And you should understand what kind of material to be used, be it cinder block, concrete, drywalls, lockers, metal, glass window. So you should have thorough knowledge of everything. So before modeling, we must understand architect by doing site visits. So if possible, watching images and videos using Google Earth, using AutoCAD files as well. So we must section the stadium by floors, and we must have each floor on a different floor plan. So when modeling, we must scale each floor alike. Why? So that all floors should align properly. And when importing walls, we must remove any kind of double walls and unnecessary materials. And when creating stands, we must create them by using the inclined surface. Also, keep any pictures or references nearby to model the building as accuracy as possible. In addition to that, you have to take care of these pillars as well, because they makes an important role during the 3D modeling and especially for RF propagation. So again, with the 3D modeling, you can obtain the visual representation of a building. This ensures the walls, right, walls, floors, etc. and scale specified are correctly represented for this building. So with 3D modeling, you can see the current layout plan, the entire building, all the floors, level of this building, selected floors of a building. And as I mentioned earlier, that stadiums are multi-level structures that contains a wide variety of RF propagation environment. The most significant area is the sitting bone. It is modeled as an inclined surface. You can see here the inclined surfaces, right? And you can see here in this also inclined surfaces, this blue area, and on the left side you can see layers, building and floors, and you can play with this in the IB wave tool. So it is modeled as an inclined surface so as to take into account the differences in the elevation between the rows of the seat. And UE in this area will have a clear line of sight to the serving antennas. That's why they are positioned above the seats, right? So these are the inclined surface. So we need to recognize that stadium is not only a multi-level but also a very heterogeneous RF environment. So what we have is a horizontal surface and a combination of line of sight, non-line of sight, and diffraction as well. So this is best analyzed if you build a 3D model of it and then allow the propagation take into account all those different RF environments, because interfering signals will be coming from all levels and from various directions. Also, the detailed 3D model is going to help quite a bit in getting an accurate bill of materials. We call it BOM as well, which is bill of materials. So because you want to deal with the cable length estimates as well. The closer you can get to the real value, the better off you will be in the long run. So making a 3D model of a venue can take anywhere from maybe 5 hours for a small venue to maybe 20 hours or more for a complex venue. So it takes a lots of time to do a detailed modeling, but it is necessary, especially for large stadiums. So proper modeling of a venue is important not only for propagation analysis, but also for good bill of material estimates, such as length of coax or the pipe. Then we have to talk about sectorization. So generally what we do in stadiums, as stadium already has dash, so we can add new sectors, we can do dash upgrade, like in Comscope we are doing from ion U to ion E upgrades. We can add millimeter wave radios add for capacity. We can add C band for capacity. But in this session, we are assuming that this is a completely new stadium. So we have to design stadium from scratch. So as I said earlier that the stadium is a densely populated venue. So we obviously can't cover the whole stadium in one sector. So we need to split that into smaller areas with lots of sectors. So in order to cover those small areas, we should have many sectors and many separate sectors. So that is how we actually handle capacity. So this is an example that I showed here is a stadium with 65 sectors. So some sectors are in the admin and at lower level, some sectors at the ball, at the concourse level, 3 sectors at the field events, and 8 transition zones, maybe at the entrance of the stadium, right, for ingress and egress. You can talk about that thing as right. So basically each sector serves 2000 to 3000 subscribers. So it is not unusual to see such a large number of sectors in a stadium. This was an assumption that was covered later on in the capacity dimensioning as well. So each sector can cover 2K to 3K subscribers. So here in this stadium, in this Mercedes-Benz Stadium, also known as Falcon Stadium, we have around 75,000 seats and we have proposed 65 sectors. Now, sectorization overlap. So what we need to make sure is that overlap between those sectors is minimal. As I said earlier in the slide before, we have around 65 sectors. If there is too much overlap between these sectors, it can increase our interference, and finally it will reduce our sign-R. And sign-R is reduced, then our throughput will be reduced, because sign-R and throughput are closely related. At high level, you can say that capacity is equal to bandwidth log 1 plus sign-R, right? According to Shannon's law. So if our sign-R is affected, our capacity will be affected. So for that, we have to use antennas that have a narrow beam width. You can see here in the figure, I have given 3 types of antenna patterns and they are grouped in pairs. The upper one is horizontal. So this one is horizontal and this one is vertical. Okay. So first one is 60-60. The second one is horizontal 30 and vertical 60. And the last one is horizontal 30 and vertical 30. So these are type of antennas with those narrow beams that you would want to use to isolate those sectors. What is the aim? Aim is to minimize the sector overlap. Again, what's the purpose of sectorization? So sectorization has dual purpose in design of a radio network. First and foremost, it increases network capacity. Why? Because each sector has its own channel cards capable of carrying voice and the data traffic. Sectors are assigned a specific areas to cover and serve a specific number of subscribers. The actual area to be covered and the actual number of subscribers that a sector should serve is a part of capacity dimension. And we may go through various parameters soon, but there may be various parameters like you can say number of channels, right? You can say data rate, then you can say type and duration of calls, then you can also say various other factors like number of seats, then penetration rate of a subscriber or a carrier, penetration rate of a right, penetration rate of a carrier, and also it may be dependent on the mobile traffic profile, right? So these are all the parameters we'll see in the capacity dimensioning as well. So, and there may be more parameters. So these are the important parameters like number of channels per sector, data rate, and the type and duration of calls and the data connection. In addition to that, we have various parameters like number of seats, carrier subscriber penetration rate, and the carrier's mobile traffic profile as well. Okay. And the second purpose of sectorization is to minimize the number of signals present in the area by limiting sector coverage. Limiting the coverage also limits the interference from non-serving sectors, and it will improve capacity, sign-R, and the maximum achievable data rate. And it is also called MADR. We'll see in the KPIs. MADR, maximum achievable data rate. So in LOS areas like the sitting ball, sector overlap minimization is achieved by using highly directional antennas. Okay, always use these directional antennas. So in order to properly size stadium networks, it is necessary to determine the number of sectors required to support each carrier's capacity requirement. Now, there are few common sectorization types. So, 2 types are commonly used. So you can see here examples of such sectorization schemes. So, first one is horizontal. This is also called horizontal, or it is also called ring type sectorization. And the second one is vertical, and it's also called wedge type. So these are commonly used where the number of sectors is not very high. So mostly when I design, I try to use this wedge technique. I like this wedge techniques because in case of this horizontal interference may be increased, but in case of this wedge sectorization, it may be possible to reduce the interference. Moreover, generally public don't have access to all areas in the stadium. So they don't move like this, right? So they move like this, right? So that's why I like this wedge sectorization. And so advantage of these kind of sectorization is that it can reduce the extensive handovers between the UEs. But if, however, the significant number of sectors are required, then hybrid ring and wedge sectorization is the best option. You can see here the examples of sectorization, which is mixed wedge and the ring, and we have around 24 sectors. Then we have this stadium design methodology. So as we have discussed earlier that stadiums are very different as compared to other in-building venues. So their design methodology is also a little bit different as compared to other venues. But steps are similar as compared to other venues. So the first step is define the requirement. So as a first step, we must define the targets for our stadium system performance. And this is done by often defining the requirements. And examples of such requirements can be what are the coverage level required, right? And it can be areas where coverage is required. So some areas you require maybe a neg 95, some areas you require neg 85, neg 75, right? And then you should also do the leakage consideration. Then you should also know the expected number of users. Then you should also know the traffic profile. Also you should have knowledge of peak traffic demand. So you should consider all these things while defining the requirement. Then we have design for coverage. So definition of coverage boundaries, sectoration areas, and the prediction of signal strength is also required. What is the aim? The aim is that where to put your antenna, where to install your antennas, right? Also various characteristics, radiation patterns, and transmit powers of the antenna must be also defined. So for this, suitable propagation model should be used. And we have discussed about the continuous wave testing. So based on that, we can calibrate our model in the IB wave, and for that, model tuning is also required. Otherwise, there is a high risk of spending too much time and not getting all the valuable samples that are needed. Then we have this design for capacity. So not only having the sufficient signal strength is required in stadium, but also the capacity. So many people will use the video call, data download, sharing the goals with their friends. So all these nodes capacity, maybe it's email, maybe it's like WhatsApp. So this will be taken as a basis for selecting base station equipment as well as suitable distribution system, which can be guarantee scalability in future as well. After that, we have to optimize the performance. So once the preliminary design for coverage and capacity has been done, antennas has to be selected, propagation predictions have been made, and sectors have been defined. Then we have to do the optimization to tweak the performance of the system and to maximize the performance, right? And in the last, we have to do the installation and the commissioning, right? And finally, we have to take measurements so that we are complying with the acceptance criteria. So these are the few steps we have to follow for the stadium design methodology. So first one is define requirements, then design for coverage, design for capacity, optimize performance, installation, and the commissioning. So these are the high level steps. There may be some sub steps as well. So, but these are the high level steps for stadium design methodology. Before going to actual sectoration, we have to talk about the PRBs as well. Physical resource block. I know you may have good knowledge of PRBs, but this is very important to refresh this because these parameters will be used during the actual capacity dimensioning, and it will affect our number of sectors which will be required for the capacity dimensioning. So let's talk about PRB. So as you know that in case of LTE, the radio frame has a length of 10 milliseconds, and each frame is divided into 10 equally sized subframe of 1 millisecond. So this frame is of 1 millisecond, 111. So each subframe is of 1 millisecond in length. The smallest time frequency grid for downlink transmission is called the resource element, and it is one symbol by one subcarrier, right? So then we have this resource block. So what is resource block? So resource block is a group of 12 contiguous subcarriers in frequency and one slot in time from the time domain, right? So this is one resource block, and data is allocated to user equipment in the units of resource block. Thus, an RB has 84 resource element. Why? Because we have 12 subcarrier multiplied by 7 symbols, which is 84 in the time domain. And in the frequency domain, a resource block has 180 kilohertz because we have 12 subcarriers into 15 kilohertz subcarrier space in the frequency domain. So it is equal to 180 kilohertz, right? But in case of LTE, scheduling is done on a subframe basis. And as I said that subframe length is 1 millisecond. So we need two resource blocks. So given that a TTI lasts for 1 millisecond of a time, the E0B scheduler allocates PRB to the users a pair at a time. So two resource blocks are allocated at a time. At high level, you can say that one PRB is equal to two resource block, and one PRB is allocated to users for a scheduling purposes. So we have 14 symbols and we have 12 subcarriers, right? So we have total 168 resource elements, right? But you should remember this, that all 168 resource elements may not be used for data, or you can say that all these 168 elements will not be used for PDSCH channel, which is our data channel. Some are overhead as well. So we have to take care of that also in our capacity dimension. And in case of 5G, you should also take care that in 5G, there is a concept of a slot. In one slot, we have 14 OFDM symbols, and on the frequency sides, we have 12 subcarriers. In case of LTE, our subcarrier spacing is fixed, that is 15 kilohertz. But in case of NR, we have various options available. It may be 15, 30, 60, 120, 240, and so on. So based on that, our carrier dimensioning will be also affected, right? So you have various kinds of subcarrier spacing, 15, 30, 60, 120, 240, and based on that, our number of slots are affected. And then this will affect our capacity dimensioning as well. So you should know this information as it is needed in our dimensioning process. Let's move to capacity dimension. So as we have discussed earlier, so let's see, I think somebody has put some in the chat box. Let's see. So for stadium optimization, yes, so IBWay is mostly for design, but yes, if you have IBM certification, then it will help you in the stadium optimization as well. So as well as signer is concerned for LT and NR, it depends on your throughput need. So signer is directly proportional to capacity. So if your signer is high, your throughput will be high. So your throughput needs depends on the, so your signer depends on the throughput needs. So suppose if your throughput needs is 10 megabits per second, suppose, and corresponding signer is maybe 2, right? So it means signer requirement in that area will be 2 dBm. But if your throughput requirement is maybe 100 Mbps, then signer requirement may be 20 dBm, right? So it depends on your throughput requirement in a particular stadium. We have signer, right? So signer is dependent on the throughput requirement. Okay, have I answered your question? Okay. So let's move to capacity dimensioning. So as we have discussed earlier that in order to properly size stadium networks, it's necessary to determine the number of sectors required to support each carrier's capacity requirement. The number of sectors per carrier depends on the various factors like number of seats, carriers, penetration rate, and the carrier's mobile traffic profile. So first one is the profile essentials. So now we have profile essentials. So here what we are going to talk about is how do we define a typical calling pattern for users in a stadium? What are the assumptions that we may assume regarding their calling pattern? What are the preferred data sessions that they will have at a stadium? So if a network is congested, if the application for some reason can't be used, then we'll treat that as a denied service. We'll calculate call denial or blocking based on the user profile and the number of subscribers. But before I go on, I just want to point something out that we use the term call blocking and the call denial, even though we are fully aware that this is a data session, and the data session really do not have denial of service like voice circuits. Instead, they have excessive delay, and when excessive delay happens, so what happens is that customer perceives the network as a slow, and they usually just abandon the application. They basically decide to either kill the window or just put a phone in their pocket and not try to use it again. So from the practical standpoint, it is those calls that were too slow. They were treated as a blocked call. So blocked is one that never really went through from one point of the user experience. So when we talk about blocking, we are talking about the percentage of attempted data sessions that have excessive delay, therefore abandoned by the subscriber. So when defining a user profile, what you need to access is what is the service type that will be used with the duration of each connection. So what is the data rate at the stadium? What we are going to assume is that not many people will be using video conferencing due to crowd noise. So we will assume 5 milli-erlangs per use. You can say for video conferencing, we are using just 5 milli-erlang because there may be lots of noise in the stadium. And as for video streaming, most stadiums ban video streaming outright. I have still made a sign like 1 milli per users, not because I am thinking that they are going to try to use it for 2 seconds and then abandon it, right? But rather, they are customers who can circumvent this ban also, right? That's why I'm using 1 milli erlang per user, right? Then when we have email browsing and data, for that I using 50 milli erlangs. Then we have browsing, 100 milliamps per user. Okay. So these are the some of the user profile. Then we have to talk about the subscriber count. So this slide is very important. So the average duration of video streaming session per subscriber may be 10 milliamps is shorter than other venues. Why? Because fewer customers use the service due to crowd noise. So most stadium ban video streaming outright due to high bandwidth required for the support. But some technical savvy subscribers may find a way to circumvent this ban. So we specify a very short connection time, like 1 milliamp for the video streaming. So most of the traffic at the venue is internet browsing and the data download with some emails, right? So it is assumed that voice traffic is carried over WCDMA while data is carried over HSPA and the LTE protocol. Okay, so this you should remember. Then we have this subscriber count. So next step is to figure out how many subscribers are we dealing with. So this is a stadium with around 60,000 seats, and I have assumed that there are 3 wireless service providers, and I have their penetration rates, and this is general assumption. I also had to make assumptions about the breakdown of their subscribers between two technologies. One is UMTS and one is LTE, right? So suppose I have total 60,000 seats and we have 40% penetration rate, and 25% goes to UMTS and 75% percentage go to LTE. So 40% of 60,000 is 24,000, right? Out of this, 25% goes to UMTS. So 1/4. So 6,000 goes to UMTS and LT will get 18,000. Same thing you can do with WSPB, wireless service provider B, and you can do with the C as well, right? So 3,000 and the 9,000. This way you can calculate number of subscribers per technology per carrier. Right? Our next step is to establish a link between the spectral efficiency and the SINAR. So we must have that because SINAR map is going to be critical when for the capacity calculation. So we will show later on why. But first of all, the table to the right is taken from the 3GPP documents, and it gives the relationship between CQI modulation and the spectral efficiency. So what we don't have is the relation between SINAR and the CQI, and that is not specified in the 3GPP documents, and it can be obtained directly from the vendor. So you can see on the left side this table CQI versus the SINAR. So for capacity dimensioning, a downlink LT SINAR coverage map must be calculated. So combining the previous two tables, we get the spectral efficiency versus the SINAR table. Okay, so as somebody was asking how much SINAR is required. So generally we consider SINAR of 6 dBm to 9 dBm as a good SINAR, but according to throughput requirement, we can choose our SINAR. So you can see here we have around 15 CQIs, and according to SINAR, so if SINAR is high, we can have 64 QAM. So 64 QAM means we can have 6 bits per symbol. 16 QAM means 4 bits per symbol, and QPSK means 2 bits per symbol, right? So this way, so when we combine those two, what we have is a table which shows modulation and the SINAR, right? And this is a big table that has 15 entries. So I simplified that to a table with 4 entries only. So CQI is 6, 9, 12, and 15. So this is a big table with 15 entries, but I have turned it into the 4 entries. So each SINAR range has a specific modulation scheme with a specific spectral efficiency value. And the dependence of spectral efficiency SINAR is important because spectral efficiency ultimate determines the maximum achievable data rate. If you know that spectral efficiency is throughput divided by bandwidth, right? So higher the spectral efficiency, higher the throughput. Then we have to take care of SINAR range as well. For example, for SINAR range between 3 and 9, we have chosen area around 30%. For 9 to 15, around 25%. For 15 to 20, again around 25%, right? So this way you can choose. So some assumption may be made about the number of sectors that can overlap, right? Because an overlap affect your SINAR. So next step is to figure out how many PRBs are needed to support those listed service types. So email browsing, video conferencing, data downloads on the video streaming throughout the stadium. So we know that what is the required data rate for each one of them. So we now have to figure how many PRBs we need for each of those applications. First of all, we have 4 different SINAR ranges, and each of those ranges have a different spectral efficiency. It means I'm going to have a different number of PRBs needed to support those service types that are listed. So for example, in range for SINAR greater than 20, let's assume this thing, SINAR greater than 20, our MCS efficiency is 5.0 0.55. And PRB data rate is MCS efficiency multiplied by number of PDSCH resource elements divided by 1 millisecond. As I said earlier that 1 PRB is 168 resource element, but not all of them are used for data. Not all of them are used for PDSCS, right? So we have to take care of the overheads as well, right? Suppose there are some overheads. So suppose we are using 132 resource elements for data and our spectral efficiency is 5.55. So our data rate will be around 726 kbps. Okay. So we are here. So, right. So we have around 726, right? So you can see here for video streaming range 4. I put here 3. Why? Because for video streaming, I need kbps of 2000. For 1 PRB, I need around 726, right? For 2000, I will need 3 PRB. So as we increase towards range 4, we need more PRBs because we have less efficiency, right? So this way, we can calculate our number of PRBs according to a particular range. So these are the inputs and outputs of a capacity dimensioning. So you should know total number of attendees as a venues, market share of each service operators, traffic profiles, number of carriers, coverage, and so on. And output is number of zones. So these are the inputs you have to put. So since theory is also already discussed, so you will get the number of sectors according to your number of subscribers and various other things like modulation, MIMO, efficiency, duty cycle, etc. Right? And then let's talk about KPIs. So first one is RF. So first one is RSRP. Right? So for the signal to be dominant at the venue, it has to be stronger than the residual signal coming from surrounding macro site. As most stadiums are open area, the residual macro signals level itself is usually fairly strong. In our example, we assume that macro LT reference signals is between NAC 80 and NAC 85. So we want that our IBS signal should be more than NAC 75 over 95% of the area, right? Then we have SINAR. So as we discussed that the modulation scheme used in LT network is directly related to PDSCH SINAR. So as high SINAR makes possible higher modulation, and higher modulation means higher throughput, right? But a large number of sectors implies numerous sector overlaps, which may cause interference and the lower SINAR. So you can see an example of 24 sectors. You see it looks very heterogeneous. So you see a lots of yellow and blue and green, and that is because, as I said, when you have high density sectorization, you really can only expect good SINAR everywhere. A really good SINAR to be very close to NTN, and SINAR gets degraded rather quickly at the cell edge, which is what you see. So same thing for the MDAR. So MDAR is directly proportional to SINAR. So you also see the heterogeneous MADR here. So SINAR and maximum data rates are closely related and interlinked. That's why the percentage of one corresponds to the percentage of other, right? So based on SINAR coverage distribution, the downlink SISO MADR distribution across the stadium is calculated. So again, guys, so this is a summary we have discussed in the class. So we have discussed about stadiums, design requirements, target areas for coverage, inside the stadiums, outside the stadium, best practices, 3D modeling, sectorization, capacity dimensioning, and the KPI.